Hi everybody, I'm the Greatest Living Inventor, and today we are doing my invention, a dry ice blender, which helps against wildfires. Okay, so this is the second time that I'm recording. The previous one was almost an hour and it was too long, it didn't upload, so I will try to make it shorter. Okay, so dry ice blender. Okay, so first of all, what is dry ice? Dry ice, and one note before we begin, the invention is not the naive idea of putting dry ice on the fire. It's not that, it's more complicated. Okay, so what is dry ice? Dry ice is a CO2 in the solid form, frozen CO2. Okay, so it's frozen CO2. Okay, CO2, carbon dioxide, has this property that maybe you know. Much of the things that I'm about to say probably you know, but I'm just saying this so that people that don't know have the necessary background. CO2 is called dry ice because it doesn't have the liquid phase. It's not like water ice. Water ice, when you heat it, normal ice you have in the freezer, when you heat the ice, it becomes liquid. It becomes from solid ice to liquid water. And after that, if you heat it more, it becomes like in the kettle, it becomes from liquid water to steam, to vapor, gas. CO2 goes right from solid and straight to gas. Okay, it doesn't have the liquid phase. Okay, so this is why it's called dry ice. So this is why in many experiments that you see, they bring dry ice if they want something cold, which means frozen CO2, because it doesn't have all the mess of the liquid. It doesn't have a liquid. Okay, so dry ice, if you put it on water, you can see in videos in YouTube, and I will put one in the links in the description of the video. There is a nice one. Can dry ice put out a fire? Okay, it's a video by Uhas. Okay, so it's a nice video in YouTube. I will put the link in the description. And the main idea in the video, that the answer is yes, but only if it's in a closed place. Okay, if, for example, if you have it tries it out in a bucket, but if the wind can come and the wind blows and brings new oxygen and takes away the CO2, then it doesn't work. Then the answer is no. The dry ice cannot put out a fire. Okay, one more thing that I want you to know, because it's the basis of everything we talk here. is the fire triangle. Okay, fire triangle. Sometimes it's the fire pyramid or fire tetrahedron, because it's when we talk about metals that are burning, then even if you put water on them, it makes it worse. For example, if you have magnesium or titanium burning, you shouldn't throw water, because the water decomposes and explodes and only feeds the fire. Okay, but in normal, like in wildfires in the forest, when this is the scenario that I'm talking about, it's only the fire triangle. So the fire triangle is simple. Let's say this is the fire. Okay, so the fire is surrounded by the conditions to make it to let it burn. So first of all, fuel, and then and they put it like in a rectangle, so it becomes a triangle. Then there is a rectangle here, which is oxygen. And then there is a rectangle here, which is heat. Okay, temperature. Okay, so basically, fire, a regular fire, needs all three. The fire itself is the combination of fuel and oxygen, but it needs also the temperature of the combustion, because otherwise, if it's too cold, it doesn't happen. You can put the so it needs all three. If you take one of them, the fire is extinguished. Okay. So fire retardants. This is all background, but we need the background. Okay. So fire retardants. Are all sometimes they don't include water, but let's also talk about water. It's like all the materials that can help us fight fires, to put out the fire. So water and foam and gels and halon and the sand. Okay, many materials that help us fight fire, that we put on fire in order to put it out. Okay, so it's like in the game that the children play when the rock, scissors, and the paper. Each one is good for another scenario. Okay, it's not like someone is good for everything. For example, water, we talked about it, that if we have metals burning, it's not good, it's bad. Or I don't know, like halon, it's now it's being put out of use because it's toxic. Okay, or like each of them has a different like foam. It contains it's basically bubbles that contains air. So for our use, for example, CO2 is better because CO2 really chokes. It doesn't contain oxygen. It chokes the fire. Or gel, it contains like bubblets, like it's bubbles of filled, instead of air, it's filled with water. So it takes a lot of water. So it takes a lot of volume. and each of them, and the sand is good for metals, but we cannot throw it on the forest because we will bury the whole forest. So you see, like from all of this, CO2 is really in our, we need this for wildfires. Okay, I'm only talking here about the use for wildfires. This is the scenario that I'm talking about. So for this scenario, like CO2 is the best. But there is a big problem with CO2, which I told you about. If the wind comes, and in the forest there is wind, it blows away the CO2, and it doesn't work. It cannot work. If we are in an office, for example, that is burning, the CO2 is good because it stays in one place. If the wind comes, the CO2 is gone and it doesn't work. Okay, so my solution basically is a way to use CO2, but in a way that it sticks to the that it stays there. Even if there is wind, the wind is good for us. So this is my the idea for my solution. And also, if you look in the fire triangle, when we use dry ice, it's both cold, frozen, and choking the fire. So we are taking care of both the oxygen and the heat. So it's better than only CO2 or any of these. Like water is cooling and the foam is choking, and so this is both, each of them basically deals with only one side of the triangle, but if we use dry ice, we take care of two, both the oxygen and the heat, because it's frozen. Okay, so I'm erasing and I'm explaining what the blender means. Okay, so remember, our goal is to use dry ice or frozen CO2, but in a way that it sticks to the trees. Okay, so the idea, where does the idea come from? The idea to the solution comes from the frozen yogurt machines. Frozen yogurt it's the machines that look like a box. That has a big handle, like a lever that you pull, or the operator of the machine pulls. Like here there is a big handle. If you see this big handle, you know it's the type of the machine that I'm talking about. Okay? Because there is another thing called frozen yogurt, which you just put the yogurt and then put above the toppings without smashing them, without making it more like filled with air, like creamy. Okay, so I'm not talking about that type, which you just put the toppings above. I'm talking about the type where you grind the, here there is like like a knife that I don't know how to draw it, but it's like a knife that rotates, and here the it puts it into the cup. Okay, so frozen yogurt, I know it's like, it sounds totally unrelated to what we're talking about, but believe me, it's related. I will explain in a minute. It's like you have, you go into the shop and you have like tanks with some materials, like you have, let's draw just one. You have, for example, strawberries. And you have, I don't know, grapes. And you have chocolates. Or cookies. And you ask for the, from the person in the shop, which ones you like, and he puts it also, he or she adds the yogurt, which is almost frozen. It's cold but not frozen, and then the machine also puts inside air, like compressed air, or from the handle. I don't know how it works, but it puts bubbles of air. Okay, so let's draw bubbles. And then the machine gives you the result, which is the yogurt. Plus inside the yogurt there are all the ingredients, but they are grounded. Like it grinds them here and slashes them. I don't know how you call it, but you feel them. It's like a homogeneous mixture. Okay, so there are small pieces of them everywhere. Okay, so in the same way, and also it freezes them. Okay, so here it's like air. Sorry. Air or gas, air, and cooling. Because this is frozen, okay? This is like why it's called frozen yogurt, because it starts out not frozen and it becomes here frozen. Let's draw it like a straight line. Okay, so here it's cold but not frozen, here it's frozen. Okay, so in the same way, in the exact same way, we should prepare the dry ice, but in a way that it will form bubbles. Okay, bubbles of CO2. Okay, so we need, and we prepare it in advance. Okay, so our goal is to make a block of dry ice with internal bubbles, with the structure of bubbles like soap bubbles. So we start with the soapy water. and we can add something that to make the bubbles last longer, like glycerol. This is what they use in bubbles, in soap bubbles, to make them last longer. So this is the water, and we have like glycerol, which I don't know how to draw. I don't know how it looks. I think it's transparent, but let's make it like it's green. And okay, so it's water with a little glycerol, which we symbolize in green. Okay, and then we have also the CO2. Sorry. Well, this will be like a tank more than a jar, but anyway, this is CO2, and CO2 we can get easily from places that where it's a byproduct that they don't want. For example, if a factory, all the factories that produce CO2, and we don't want that, we have a problem of too much CO2, so we take from them CO2, okay, in right where it's coming out of the chimney or whatever, and we collect it, so it's not expensive. And the water is in, it's mostly CO2. The block that we will prepare is almost all of it is CO2, and a little bit of soapy water and glycerol. So the whole thing is cheap. Okay, plus cooling. And the gas is here. Okay, the air is, instead of air we have the CO2. And the cooling means it turns into dry ice. So what we get eventually is a block. Okay, this is like a block. Like it's supposed to be a big block. I don't have room to draw it, but it's like, I don't know, 1 meter cube, filled with an inner structure. Because of the slashing inside of the knife, it has an inner structure of like bubbles, but frozen bubbles. And mostly CO2, frozen CO2, and a little water. Okay, so I hope you understand. This is the whole block is dry ice, but there is an inner structure of bubbles of CO2 that are frozen. Okay, so basically we will call this dry ice block, but the block contains bubbles inside. When you heat it, it turns into gas, but the CO2 releases bubbles of CO2. Okay, so okay, so now all this was to get the block. Okay, this is. This is what I will call all the time the blocks. Okay, so we have blocks of these, and we prepare them in advance. Okay, so I'm erasing. Okay, so let's suppose, and also we can erase the title. Okay, so first of all, what happens today? Today, if the firefighters come and there is a wildfire, let's say there are many trees that in the forest, and the trees have some branches and leaves. And the firefighters come with their like fire truck, and the fire truck contains foam or gel or water, and so the firefighter is shooting with a hose or something water on whatever he can reach. Okay, so he can reach only this far. So he can, if the fire is here, then he's fighting the fire that is here. Okay, but if the fire reaches further, then he can't reach it. Okay, he can only reach to the edge of the forest, because here it's like very hot and too dangerous. But in my system, you have another track, which is like, first of all, you make the blocks of the dry ice with the bubbles inside, and you have a refrigerator track. Okay, so this is the refrigerator. Let's call it fridge, or even freezer. It's more accurate, freezer. The dry ice is freezer. The dry ice forms in the critical temperature is minus 78.5 degrees Celsius. Okay, minus 78.5 degrees Celsius. So this is the temperature, even less. We need here like a few degrees less, because if there is some malfunction, we don't want it to explode in the car. So the track contains blocks, okay, and they are cooled. Okay, it's like a freezer. Okay, and here we have another track which doesn't have to come close by, and the other track is like a catapult. Okay, catapult, or like a trebuchet. Okay, so you know what the catapult or trebuchet is. It's like there is two A structures here, and a long arm and weight, and or let's draw it before it fires. So before it fires, it looks like this. Here there is a big weight, counterweight, and here there is the payload that you want to shoot, which is the dry ice. Okay? And when you release here the whatever holds it, it shoots the dry ice. It's more complicated, like it has a sling, but never mind. Let's say it's a normal catapult. It shoots the dry ice. It's like, I don't want to fuss over how a trebuchet works, but it has like here a place to hang whatever it is, and it's like it whips over, so it's even more fast. But let's say it's just shoots it, and this is like a medieval weapon. This was used for hundreds of years in the medieval times. So we have a block and we shoot it. It can even be from a mountaintop or whatever. It doesn't have to be close. It's not like this that has to be very close. This can be far. This can be like even hundreds of meters away. Okay, so they are in a safe distance. So it's much safer. So they shoot it into the forest where the heart of the fire is, where the main fire is. Okay, and it falls here. And once it falls, it's hot in there. Okay, so the block releases the bubbles. Okay, so if the block looked like that, and it had this structure of bubbles. So when it approaches the heat, like let's say here is a heat, it melts it doesn't melt into liquid, but it melts, it sublimes into gas from the outside to the inside. So this remains cold, but here it gets hot, so it breaks apart and releases a bubble. Okay, so from here we have it. At first it looks like this, but eventually it releases a bubble. Okay, filled with CO2. Okay, this is CO2. And when it gets close to the fire, it's too hot for the glycerol, so the glycerol breaks apart and releases the CO2 onto the fire. Okay, which is cold because it just above the 78 or something, minus 78 degrees that it were, and it's suffocating the fire. So if it's near the fire, this is what happens, and it extinguishes the fire there. If it's not, it breaks apart from the ambient temperature, from the normal temperature of the forest, which is not that cold. It's like in our room temperature, and it breaks apart and it forms the bubbles, but they don't explode from the fire. They just stick to the trees, okay, because they're like soap bubbles. So the bubbles, the very small bubbles, I'm just drawing them big so you can see them. They stick to the trees. And if the wind is like in this direction, then the fire goes in this direction, but also the bubbles go in this direction. And when the fire reaches them, they explode and they burst and they put out the fire. Okay, so now I will read it to you if I have time. I don't know here, the software doesn't show me how much time I talked. I will try to read it to you so you have the whole picture, which now you understand because you saw the whole process. Okay, so the main idea is if the wind is like in this direction, it helps us. It's not like normal CO2 because it forms bubbles that stick to the trees and the branches and the leaves. So if the wind goes that way, the fire goes that way, but also the bubbles goes that way. So the solution follows the problem. Okay, so suffocating wildfires by catapulting dry ice, frozen CO2 blocks that were prepared with built-in soap bubbles of CO2, like frozen yogurt blender mixes, frozen fruits inside. The bubbles cling to the forest trees, so the CO2 doesn't disperse in the wind. And of course, I'm just saying we can drop these from a freezer airplane. Okay, so we can also shoot it not shoot it, but drop it. It's even simpler from an airplane without danger to the firefighters. And it's not like water that you need a lot of volume. These are compact. They just need the cooling freezer. Okay, I take an old idea that has a serious drawback, the dry ice on fire, and put a new twist on it so that the drawback is gone. The old idea is to deprive the fire from the oxygen it needs and chilling the fire below the temperature it needs to ignite at the same time using dry ice, frozen CO2. The drawback is that the wind would carry the CO2 away. That is like the old solution. Here it's the opposite. That's why until now this idea was not adopted by firefighters in open areas like wildfires. My original twist, quote unquote, is to not just freeze the CO2 but also foam it with liquid soap while it's chilled to its freezing point. And so we will have tight solid blocks of self-releasing, in parentheses, when it goes through sublimation in the heat of the fire, it was catapulted into, solid blocks of self-releasing CO2 bubbles that will rise from the heat and stick to the trees using the wind in exactly the same direction that the fire is going the strongest. The cure will follow the disease automatically. Unlike firefighters that spray foam or water from a hose in the outside of the fire, here with the dry ice blocks we can operate from the inside of the fire and fight it from within. I think the best solution would be to catapult the blocks, but we can also drop them from a plane or helicopter and even leave them on the trail where the fire is approaching, which is cheapest. The blocks are not manufactured on the spot, They are made in advance in a factory and can be driven with a truck that has a freezer. Sort of like an ice cream truck, but that can maintain a temperature below CO2 sublimation, which is minus 78.5 Celsius. In parentheses, and of course a safety margin, close parentheses. Also coming to the site will be trucks that carry catapults, like in the Middle Ages, when they made a siege on a fortified castle and flung big rocks. Okay, this is the trebuchet. And here is a video that shows, I told you about the video, I will put it in the links. And here I explain also about the frozen yogurt, which I'm not going to read to because I told you already. And I put links also in the description. So thank you very much, and I will see you in my next invention. So thank you. Goodbye.